Hello, I'm Tom Cotter. For my final major project, I aim to tackle the problem that current standardised measures of the speech transmission index are non-inclusive of the human auditory system's binaural advantages. For example, a noise source on the right of the head will have its mid and high frequencies shadowed at the left ear, creating a level reduction which will improve intelligibility for a speaker on axis of the listener, in a condition known as better ear listening. Extensive and successful research has already been complete into implementing head and torso simulators. However, these are cumbersome and expensive. Therefore, this project aims to implement binaural advantages through a binaural decode of a first-order ambisonics microphone. It's essential that a single model will work in all environments. Therefore, steeper measurements were conducted in hemianechoic, semi-reverberant and reverberant environments. The target source was placed on axis of the head and torso simulator and ambisonics microphone, with a noise source rotated at two masking levels in 15-degree increments. Measurements were also complete in accordance with BS 60268 Part 16, since it's essential where a binaural auditory system is not advantageous, results resemble those made with current standardised methods. Ultimately, it was concluded that the resolution of first-order ambisonics was too low, creating localization errors in the encoding of the sound field, which increased as reverberation time increased and masking level decreased. Furthermore, the low resolution also spread properties of the head-related transfer function over a wider azimuthal range, further decreasing accuracy. With this being said, a relative level of accuracy was still achieved, suggesting binaural decodes of higher order ambisonics microphones are likely to yield accurate results. From this investigation, further conclusions can be drawn to infer future investigations. Whilst parametric decoders perceptually improve the accuracy through extracting perceptually meaningful parameters from the sound field, they encapsulate the remaining diffuse field as an omnidirectional component, as can be heard in the following listening test. This causes significant underestimations in intelligibility of the shadowed ear. Therefore, linear decoders must be used. In linear decoding, head-related transfer functions which yield the least error in time and level from known spatial cues are selected. In the investigation, it was found for azimuths of partial shadowing, accuracy increased by around 3% when ignoring timing errors above 3 kHz in favour for a reduced level error. Accuracy at azimuths of partial shadowing was also increased through using diffuse field correction. In the context of this investigation, this essentially increases the level of noise at the contralateral ear to reduce interaural level difference. However, this meant for frequencies where opaque shadowing of mid and high frequency occurs, noise was present in the contralateral ear which shouldn't have been, which can be heard in the following listening test. This ultimately led to a 16% decrease in the accuracy of the decoder. Diffuse field correction also increased accuracy in diffuse environments, suggesting that anechoically captured head-related transfer functions overestimate spatial release in diffuse fields. Not only do binaural decodes of ambisonic microphones have commercial and practical viability over head and torso simulators, they allow acousticians to import personalised head-related transfer functions tailored to their projects. Secondly, the decoders can rotate their look direction virtually via MIDI, meaning intelligibility can be predicted for any given look direction from a single recording. The most interesting part of the project for me was the binaural decoders, as they contain lots of intricacies as well as ambisonics and digital signal processing being new areas to me. For this reason, it was also the part I found most difficult, as it was a very steep learning curve, and to understand why the decoders were returning the results they were, trolling through multiple pages of mathematical formulas from multiple sources was required to correctly interpret what was happening within the decoder. It was also very difficult to find a head-related transfer function set of a high enough resolution associated with the head and torso simulator used in the investigation. It was important to do this so that the independent variable was the encoding and decoding of the sound field, but took significant time and effort to find one. Overall, I was really happy with the outcomes of the project, and I would like to repeat these measurements using a higher order ambisonics microphone. Thank you for taking the time to hear more about my project, and please do not hesitate to get in contact if you have any further questions.